The effects of nutrients on decomposition are largely indirect, mediated by carbon quality of substrates. So nutrients are important for determining the rate of decomposition, but it's generally an indirect pathway, not a direct pathway. So if we think about nitrogen as being limiting to decomposition, the nitrogen concentrations tend to be a good predictor of how fast something decomposes. This here is a graph of the relationship between the lignin to nitrogen ratios of litter and the decomposition constant. So on the x-axis here, we have a ratio of the amount of lignin to nitrogen that's present in different litters. So relatively low lignin to nitrogen ratios means you don't have a lot of recalcitrant organic matter and you have a relatively high amount of nitrogen. Those should be relatively labile. On the other end of this spectrum, you have a relatively high ratio, so lots of lignin, not a lot of nitrogen. So this would be a relatively low quality substrate. On the y-axis, we have our decomposition constant, and those are K values. So again, a K value of 0.8 means that you're going to have a relatively fast decomposition and a high exponential decline in mass over time, and 0.1 means that it's going to be relatively slow decomposition, a slow exponential decline. So when you take a look at the pattern, it's those litters that have a low lignin to nitrogen ratio, so a lot of nitrogen relative to lignin, that decompose relatively quickly. And those that have a relatively high ratio of lignin to nitrogen that have a relatively low decomposition constant. Don't lose a lot of mass per unit time. Now microbes decompose organic matter to acquire nitrogen. So in addition to decomposing organic matter to generate energy, eventually, they also do that to acquire nitrogen. As such, adding nitrogen to litter can often reduce decomposition. So when we think about what the effects are of adding nitrogen or differences in nitrogen availability, in some cases it will increase the rate of decomposition, but in other cases a lot of recalcitrant organic matter gets decomposed in order for microbes to extract the nitrogen that's in there. And if you add nitrogen to that litter, or nitrogen becomes more available, there's really no energetic benefit to microbes to decompose that litter. As an example, this is a graph that shows the amount of heterotrophic respiration, which is essentially microbial respiration in soils, relative to net primary productivity. So this is a productivity gradient and these are for different forests. So when you look across forests, here's differences in NPP, grams of carbon per meter squared per year. This is how much carbon is produced in those forests, low fertility, high fertility forests. On the y-axis, we have heterotrophic respiration. And this is heterotrophic respiration from the soils, grams of carbon per meter squared per year. These soils, or the forests, some of them were measured under control conditions and some of them under elevated conditions. And if you take a look at the control respiration rates, there's a certain ratio between how much carbon is respired to how much net primary productivity there is. The nitrogen forests, or the forests where nitrogen was added, show a shift, not necessarily in how much productivity they have, but definitely for a given amount of productivity that you're going to have lower heterotrophic respiration. So you go to a forest, you add nitrogen to that forest, you'll see NPP change, but when you look for a given amount of NPP, there's going to be a decline in heterotrophic respiration. The microbes stop respiring quite as high. And part of that reason is that they're not decomposing a lot of those recalcitrant organic matter structures that they would have in order to acquire the nitrogen. Without the need to acquire nitrogen from those compounds, there's no reason to break them down. So that's often an external factor that determines decomposition rates. And plants can stimulate decomposition near their roots. Here is a diagram that shows root and microbial processes in the rhizosphere and the impacts on soil organic matter breakdown and nitrogen dynamics. So as a root grows through soil, it tends to have a cap that protects the root tip as it pushes its way through soil. All of these cells that are protecting the root are lost to the surrounding soil, and that sloughing of relatively labile material is an input of carbon that microbes can use to grow with. In addition, near the tip there's root exudation, so there's the input of relatively labile carbon substrates also into the soil. And this root cap material and the exudation stimulates bacteria. And so this is the area in the soil that you have rapid bacterial growth. Because there's rapid bacterial growth, a lot of nitrogen is acquired from the soil. So any available nitrogen tends to get sucked up by microbes. In addition, once nitrogen becomes relatively poor, they tend to break down soil organic matter to acquire more nitrogen. So they'll go ahead and break down soil organic matter and immobilize that in their tissues. Once roots shut off the supply of carbon, so there's no more root cap carbon, there's no more exudation, suddenly things change a little bit. So you'll have a buildup of microbes in this zone, and then protozoans and other microfauna will move in and start to graze down that bacteria. That causes excretion of nitrogen, and a large proportion of the mineralization is just microbes being grazed upon by protozoans. A lot of inorganic nitrogen and organic nitrogen is made available, and the roots can suck that up. Now, after the predation is done and grazing is done, there's still not a lot of carbon around, and these bacteria starve. And as they do that, they tend to mineralize nitrogen or release it. And again, that's a source of nitrogen to roots. So we have these different zones as roots grow through soil. They generate a rhizosphere. Root cap carbon exudation tends to be highest near the tip of the root. And as a consequence, you get a mobilization near the tip and a lot of breakdown. Protozoans will come through in other organisms and start to graze down the bacteria, and that causes excretion of nitrogen. But then also the bacteria starve when you shut off the carbon source, and that causes mineralization of nitrogen. And this is a zone of nitrogen uptake for a root growing through soil. Now I'll say there's a lot more to learn about decomposition that I can cover here, and it's going to be important to re-emphasize, to go through and read this section on the book, not only to reinforce the concepts that we talked about here, but also to spend time to get a little bit more in-depth understanding of it so that the generalizations that are covered here are more apparent.